Hi, I'm Florian Auer from the University of Augsburg, and I will present to you a perspective on code submission and automated evaluation platforms for university teaching. Acquiring programming proficiency still remains a matter of continuous practice, and professional guidance remains a key aspect for success. In-person sessions allow teachers to react to the individual issues of students and thus enable better progression. Therefore, guided practical courses on basic and advanced topics play a major role in teaching at universities. A crucial bottleneck in practical courses is the submission and evaluation of programming code of the course participants. Submissions of solutions for tasks and subtasks are usually the basis for deriving grades and therefore need to be documented. An often seen method is either sending the code by email or copying files to a USB flash drive, followed by a manual review by a tutor or teacher. For obvious reasons, this method is not only time-consuming and error-prone, but also tedious and can easily be undertaken by a platform with included automated evaluation. Because of the current COVID-19 pandemic, the face of teaching changed rapidly from in-person meetings to virtual sessions. Online tools now have to fill the gap left behind by not being able to give direct feedback on problems and errors a student might encounter while solving programming tasks. Providing the utmost verbose feedback is crucial for supporting the students in their progression. Therefore, I will provide a perspective on how a submission and automated evaluation platform can help to facilitate university teaching, especially in practical courses. For the submission and automated evaluation of programming code, we developed our platform Missit CMS. It is based on an existing contest management system called CMS, which development is discontinued. On our platform, it is possible to define several tasks for which the students can upload their solutions. Those solutions are then run with different parameters. To determine the correctness of the submissions, certain checks can be implemented, ranging from a simple comparison of the output of the run scripts to more comprehensive tests performed on the in- and output data. This is necessary if the results of the program is dependent on changing input data or as a random component to it. In both cases, it is possible to report a student under which circumstances the submission fails and which errors occur while running their code. This feature not only is valuable to the students, but also reduces the time and effort teachers have to invest in testing. Third-party modules, libraries, or frameworks are often required for solving complex tasks. Thus, our platform supports specifying predefined lists of libraries and modules for certain tasks. Those are automatically loaded and integrated into the container environment when the tasks are evaluated. Running external code on a local machine always includes security issues. To reduce and even avoid potential risks, the submitted source code is evaluated in a secure environment. On our platform, this is realized using isolate containers. Although we taught Python in our programming courses, the secure environment is not limited to this programming language. The front end for student submission of our platform is kept quite simple. The students find an overview of the exercises along the required course materials. Solutions of an exercise can be uploaded and submitted, and the results of the evaluation and the reached score will be displayed. In case any errors occurred, details of the evaluation can be accessed, including error messages and failed evaluation checks. This helps the students to revise their code submissions and will guide them to the correct solution. Providing a platform for code evaluation is also limited by the available server-side resources. Each submission has to be evaluated, and with an increasing number of students, also the demands and computational capabilities are growing. Basic approaches for executing submissions in parallel tend to fail due to the logical dependencies between subsequent program tasks and lead to more sophisticated queuing strategies. To surpass those limitations, it is possible to define several workers that are responsible for evaluating only a single task. Submissions are queued and distributed over those workers to balance the load of the system. In the admin panel, teachers have an overview of running and scheduled tasks and even can activate and disable available workers. Executing code in a sandbox comes with some downsides. Required input data must be mounted within the containers to be accessible for the scripts. Furthermore, the results, so the output of the run scripts, and occurring errors have to be stored not only for documentation purposes, but also to provide the previously mentioned feedback for the students. To accomplish this, it is possible to define specific directories to be mounted within the sandbox on a task-specific level. Proper practical courses usually take place over several weeks or months, with a significant amount of lecture slides, exercises, example code and code fragments, and different kinds of data provided. Unfortunately, it is not unusual that those are scattered across several platforms. Our platform, therefore, acts as a hub to consolidate different documents for students. To not overwhelm the students with the huge number of files at once, it is also possible to unlock those files needed for the current and previous days. The source code for MISIT CMS is available on GitHub and published with the open source license GPL version 3. The setup of such kind of a platform tends to be not quite simple in terms of software dependencies needed to be installed, and databases have to be prepared and structured. To simplify this process for others, we provide a Dockerized version of MISIT CMS that reduces the efforts almost to a one-click solution. The different components are organized with Docker Compose into different containers, including the underlying databases to be initialized on startup. We deployed our platform in 3 practical courses over several semesters and thereby gradually improved MISIT CMS. The course was aimed at teaching basic and advanced Python programming skills and was focused on implementing biomedical applications. Our experiences from a teacher's perspective are that after a short initial period in which the students require support in interpreting eventually occurring error messages, the feedback provided by our platform was sufficient to enable them to work largely independently. Each course day had a dedicated topic for which the corresponding materials were provided on our platform. New topics were activated on the day firstly needed, which then facilitated the start into the new topic and lead them directly to address the exercises. Since the exercises had not to be checked by a teacher for each student individually, not only the course could be held with less staff, but also the obtained time could be spent on providing better individual support of the students. The reduced workload affected a reduced stress level of the tutors during the course, which was generally appreciated. However, this was paid for by a one-time work overhead during the preparation phase, since the exercises not only needed to be prepared, but also integrated into the platform. Choosing a suitable specificity of the test cases was particularly one of the persistent problems. A simple comparison of the results of the user submissions to a predefined solution turned out to be sufficient in many cases, but often it was necessary to create custom tests and even refine those over the course. In other cases, ambiguous solutions or rounding errors had to be taken into account, which also leads to more sophisticated checking. In general, the usage of our platform was a great improvement in contrast to previous courses, which depended heavily on manual evaluation. Besides our own experiences, we were eager for feedback from the participants of the practical courses. Therefore, we designed a retrospective survey to capture their point of view. It was conducted anonymously, and out of 25 students who completed the course, 9 participated in the survey, which equals to 36%. The subject of the survey was functionality, usability, transparency and feedback, the code submission process compared to other practical courses, and the retention of the platform for this course. While the basic functionality of our platform was perceived as commonly satisfying, the usability shows a clear trend towards being more positively accepted. The transparency of the evaluation of the task was experienced generally impartial, with a slight tendency to the positive side, whereas the automated feedback on the results and error messages seems to drift towards the contrary. Although the majority is quite neutral or even positive towards an SAE process, the opinions spread from great approval to preference of traditional methods. Nevertheless, the majority of the participants recommended the further usage of our platform for this practical course, or at least supported the recommendations. Only one student expressed refusal towards the usage of an SAE platform within this course. However, the low response rate to the survey, in addition to the readily comprehensible number of participants of the course, lowers the expressiveness to some extent. Our own experience, as well as the feedback of the students, show that further enhancements of the test case's specificity and more verbose feedback messages to the students are required. This will help to tackle the shortcomings reported for transparency and automated feedback. With additional improvements in functionality and usability, Method CMS could be extended towards a platform for code execution and interactive computation, including Jupyter Notebook-style features. Since our platform already acts as a repository of the course materials, even further extensions towards a massive open online course is imaginable. An important topic not addressed yet within Method CMS and SAE platforms in general is checking for plagiarism. Therefore, an automated validation could be included, which compares the submitted code against the submissions of other students to determine shared code fragments or whole blocks of code. This can be extended even further to a check against common online resources like Stack Overflow or GitHub to avoid blindly copy and pasting third-party solutions. Through utilizing Method CMS for university teaching, as well as conducting a retrospective student survey over the last 2 years, we were able to identify multiple positive and negative aspects. The core benefits were the robust, transparent, as well as automated code evaluation, reducing the workload of teacher grading, the scalability, and the utilization of a structured as well as powerful platform for coding courses. Method CMS can act as a hub for course materials and also provides capabilities for archiving code submissions. However, we encountered challenges like an additional work overhead for creating automation-suitable assignments, handling or accepting various solution strategies and possibly coding errors, and as well as the requirement of a stable IT infrastructure. Here we introduced an implementation of a code submission and automated evaluation server for student programming assignments and discussed positive and negative aspects of these systems for university teaching. Our implementation, Method CMS, integrated key features like a student-friendly web interface and learning environment, scalable and secure code execution environments, dynamic integration of teacher-defined tasks, support for multiple programming languages, and automated feedback for students. In summary, we concluded that an automated submission and evaluation platform for programming assignments requires continuous development and adjustment, but allows highly robust, structured, as well as scalable student code evaluation, which reduces the workload of teachers and which resulting transparency is appreciated by students. With this and the references for further reading, I want to finish this presentation and thank you for your attention.